So MathOptInterface and JuMP 0.19 very much started at last year's workshop. I'd say the motivation was lots of questions of this form. JuMP is great, but how do I do X? So X could be, how do I add support for a new type of constraint? Let's say
Can you go back a couple slides?
This. How do I add support for a new type of constraint? So complementarity constraint was a specific request that we got. How do I combine NLP constraints with conic constraints? This directly addresses the new API that will be available in the next version of Nitro. How do I delete a constraint or variable? This has been a very long-standing request that we haven't been able to address because when we created the API, we indexed variables 1, 2, 3, and it's hard to delete a variable when you've decided to index variables like that. Sorry. How do I test if a solution is feasible? We don't have this concept currently in JuMP. It's very much tied to, you give the data to the solver, it gives you an answer back, and you hope it's feasible, but there's really no validation of that. We don't have the infrastructure to validate that. I'd say in general, you should validate this because solvers are very happy to give you solutions that don't satisfy the feasibility tolerance, or at least not what you thought the feasibility tolerance was. So this will be a pretty useful thing to have around. How do I modify coefficients in the constraint matrix? JuMP was designed to be basically very little overhead, as fast as using the Garobi C++ API directly. These are something that you could do in the low-level solver APIs, which we cannot currently do in JuMP. How do I provide a dual warm start? Here's another thing that doesn't come up until you start supporting conic solvers, and conic solvers that use first-order methods, and the first-order methods are pretty sensitive, can be sensitive to the starting point. You might want a warm start from a previous solution. And JuMP until now has only had the concept of a starting point for the primal, but not for the dual. It's useful to have both. Another thing is, how do I access the IIS from Garobi? So when you solve an LP or a MIP, some commercial solvers support returning a minimal set of inconsistent constraints, and that's a nice tool to have when debugging infeasibility. We didn't really have infrastructure to dig in and ask for a solver-specific attribute and get that result back cleanly through JuMP. How do I distinguish when a solver stopped because of a time limit and it has a solution or it doesn't have a solution? So this comes up when you're starting to write hybrid solvers in Julia. You're using solvers as a subproblem, and you need to know, you set a time limit on them, you really need to know what happened. Right now, the MathProg base status, we have time limits. We don't have a way to communicate if did I even find a feasible solution? Did I not find a feasible solution? So this was an issue with our status reporting system. Another fun status that I like talking about is Cplex MIP optimal infeasible, which means that Cplex, you gave your problem to Cplex, it ran pre-solve, it solved the pre-solved problem to optimality, unpre-solved it, and then decided that the solution it got was not feasible, but that's what it returns. And this is again a tricky situation. It comes up. I think, Chris, did we see this when working on Pyrito? Yeah. So it comes up when you're solving lots of subproblems, and you need to design a robust solver to handle what your subproblem solver can deal with, and this could just pop up sometimes. And the reason we haven't been able to address all those questions before is basically how we designed JuMP from the beginning. We started off with a solver abstraction layer called MathProg base. That's how we interact with all the solvers. It's an API that says this is the interface that the solver has to support, and if you support this interface, we can talk to your solver. And a lot of, basically all of the issues here are structural issues with MathProg base that don't let us easily answer these questions. So last year's workshop, we decided to drop and get rid of MathProg base and do something new. And this is called MathOptInterface. So I'll give a very high-level idea of what changes, and I'll get into some of the details in my talk. We have an entirely new representation of what is an optimization problem. And this is a much more extensible way to define constraints. It lets us define new classes of constraints by defining new functions and new sets, and I'll get into that shortly. We have an interface for attributes, a very clear way to ask a solver for a property. Here's, I want this property of this constraint, and that could be, does this constraint participate in the IIS? Or here, let me set this property of this constraint is the warm start for the slack on this linear constraint. Some solvers might want to have that property, so we can let you pass that through with attributes. We have a new status reporting system. We have non-consecutive variable indices and constraint indices, which now lets us delete things. We have removed the definition of callbacks. Previously, MathProg base defines an interface for callbacks that is implemented by Cplex, Groby Express, and GLPK, a little bit on the skip side also. But we realized that callbacks are too much tied into how the solver actually works under the hood. You need to understand which properties are available at which time, and to make any sort of rigorous statements about I implemented an algorithm and it runs this callback and this callback provides this information, you need to know you need to know solver specific details, and we weren't able to abstract over those successfully. So this was motivated by the work in Pajarito, where different solvers had different interpretations of lazy constraints. When are lazy constraints actually applied? What are the optimality tolerances? What are the feasibility tolerances applied to lazy constraints? If you add it during the solve, does it really guarantee that it will be satisfied at the end of the in the solution you get back? It's a very solver-specific property. And we decided that we need to take a step back and do solver-specific callbacks. So callbacks will be available through solver-specific interfaces. Nonlinear optimization, this is basically the main piece that we have not changed much at all. If you take a look at the old version and new version, the representation of nonlinear functions is basically the same. We've tweaked it to fit it into the MOI architecture, but the basic representation, the callback API for AD has not changed at all. Okay, so how do we define an optimization problem? This took a lot of iteration. We had some pretty long discussions in last year's workshop. What we settled on was to say that an optimization problem, first of all, we're only considering scalar variables, and for the moment real value, that's not too much of that's not baked in too much, but for the moment real valued variables, we minimize an objective function, and the way that we represent constraints are that some function applied to the variables belongs to some set. So every single constraint is of this form. There are no variable bounds outside of the way you represent variable bounds are through this constraint. The way you represent integrality is through this form. Everything fits into here. And this is a concrete form. These functions will be abstract function objects, and the sets will be abstract set objects. So what are the basic functions that you can deal with? So you're free to define your own function. There needs to be some agreement between the user and the solver of which functions to recognize. So we've defined a standard set of functions that covers what we were able to previously model in MathProg base. You can think about adding more. You can think about adding piecewise linear functions. You can think about all sorts of things, but to cover what we have previously supported, we define one function that this function takes a vector of x and it returns you one component of that vector. So we call that the single variable. You can think of it as a projection. We just call this function single variable. It projects onto a coordinate of a vector. So if you want to add a bound on a variable, if you want to add integrality constraints, you would select the variable by this function. Vector variables is a projection onto multiple coordinates. So if you have a function, let's say a SOS constraint. SOS is a combinatorial constraint on a set of variables. You would probably choose the vector variables function. Scalar affine function, scalar value defined function. We have vector value affine functions. These are useful for specifying conic constraints. So you would say that this AX plus B belongs to some conic set. That's how we would represent that. And we have scalar valued quadratic functions and vector valued quadratic functions. This is the basic set of things that we can use to represent everything that we've been able to represent in JuMP so far. So the actual definition of the functions, first of all, we represent variables with indices with just a type-safe wrapper. So a variable index is an integer, not necessarily consecutive, but it's just an integer, and we use a wrapper around that for type safety. And then the definition of a single variable function is, well, you just give it the variable index. That's easy. Scalar affine functions. We iterated on this recently. This struct previously had three fields, one with separating the components, the indices from the coefficients. We decided to put the indices and the coefficients together in pairs and the scalar affine term struct, so we don't have to worry about these vectors. We never have to validate that the vectors have the right length. You know that with every index you have a coefficient. So now the definition of this is we have a vector of terms and a constant. Not too hard. Some of the sets that we came up with for the scalar valued sets, scalar input sets, less than, greater than, equal to, an interval. Second order cone is a vector valued set. The set of integers, the set 0, 1. These are a few of the sets that you can that we've defined in MOI. And the definition, pretty straightforward. For example, the less than set, you just provide your upper bound. Second order cone, the only parameter is the dimension. And the 0, 1 set has no parameters. It's just an object with no fields. Okay, so now you can ask the question, I have this constraint, which pair of function and set do I use? So if you're modeling with MOI, this is probably the starting point how do I represent my constraint? With linear constraints, it's pretty straightforward. If it's AX less than U, for example, you would put your scalar affine function. You would choose a scalar affine function, and your set is less than. If it's a box constraint on a scalar affine function, use the interval function. these constraints have a special meaning. They're variable bounds. So if you provide a single variable in a less than set, then all of the solver wrappers so far will interpret this and provide it as a variable bound. But at the MOI level, these are the same objects. The transformation into bounds happens at the wrapping level. Some other things, what you can do with quadratic constraints, you can define convex, non-convex quadratic constraints. We can now define bilinear matrix inequalities. This was a set that Benoit had wanted to play around with just by taking a vector quadratic function and say that it belongs to the positive semi-definite cone, which is another set that we've defined. So that's how you can get to some more esoteric constraints just by combining standard sets, standard functions and sets. Please interrupt me at any time if there are questions, because better to ask them when I've just talked about the topic. Yep.
This bilinear matrix inequality, are you referring to the like Gillespie vectors and everything?
So I mean, so bilinear, it doesn't need to be bilinear. It could be any quadratic vector valued quadratic function. Take a set of quadratic functions, stack them into a vector, and say that this vector has to belong. When you rearrange the vector as a matrix, you have to say that you want this matrix to be positive semi-definite.
So you can also represent matrix like functions or variables as vector of that.
Yes. So we do encode matrices as flattened vectors. So, for example, we actually have two definitions of the positive semi-definite cone, or maybe three. One is, I think we have one with the full matrix, n by n. We have one with the either the upper or lower triangle, and then we have a different definition, which is we got rid of that? Okay, we got rid of that. There's an alternative definition that I think we had for a while where it's a rescaling of the positive semi-definite cone so that the vector valued version is actually self-dual. So you rescale the off diagonals by square root of 2. We did get rid of that. So yeah, there's a little turn of deciding what's the canonical way to represent these sets.
Nice.
Yep.
So you spoke about variable bound. I guess you meant bounds on variables, because variable bound can have a different meaning. Maybe it's
Bounds on variables.
Yeah, but also we would like to see variable bound in the sense that if the variable take positive value, then it's greater than the threshold or things like that, or mixed integer set.
So do you mean like semi-integer, semi-continuous?
Yeah.
Yeah. So we have semi-continuous and semi-integer as sets. So you can say this variable belongs to a semi-continuous set, which is exactly the union of either 0 or an interval, or 0 or the set of integers between these two values.
And the mixed integer set, where it's an integer number of times a constant plus a continuous.
Integer number of times a constant.
Plus a constant.
Not sure I understood.
That's a constraint.
Yeah, but
You could define,
yeah.
so you could define a new set that was that set and just like.
Yeah, okay, so there's a very good question is what is the canonical way to define, like, which sets do you decide to support and which sets do you tell the user to model? You should use this set to model, or
In a sense, go like in the constraints programming community where there are special constraints. In initial programming, we could go a bit in that direction.
I agree, and we've designed this API to let you go in that direction. We haven't defined esoteric sets yet, but the API lets you move in that direction. So you're free to define your own set, and then if you write a solver that recognizes that set, the users are free to model with it. So it's an agreement between the user and the solver which sets you want to, which sets are going to work. Yep.
Maybe as an example, so Gurobi just introduced constraints like max of a vector equals something and like absolute value or something, would the right place to maybe define those being Groby.jl or something?
Yes. I don't know if that's the right package, but yeah. So to represent specific constraints in Groby, Groby could define its own set, and a user using JuMP or MOI could write down that constraint, and it would pass that set to Groby, and the solver wrapper would recognize, okay, this is the graph of the max of two variables, so I'll encode it, I'll send it to Groby like that. So it's designed to be that. There are a lot of open questions. There's a lot of ways to pose the same problem, and actually I have a slide on this later. But we've designed the API to let you explore that space. So we haven't fixed what you can model and what you can't model. Yeah.
You mentioned the matrix is flattened out. What about sparse matrices? Are these supported in any way?
Not directly. You could encode a set to interpret the input as a sparse matrix. To unpack the input as a sparse matrix. That would be the most direct way. Yep. We don't have any solvers right now that recognize sparse matrices as objects, so we haven't supported that. Okay, so actually I mentioned a bit of this, discrete and logical constraints. So if you want to say that at most one component of a vector can be non-zero, you would say take the vector of variables to extract your subvector and say that it belongs to the SOS1 set. And if you want to write a solver that supports something fancier than SOS1, you're welcome to define that set. So how do you go about adding these constraints? Here's a little peek of the API, not too simple, not too complicated. Yep.
Well, the extra, so the idea is to modify, to create sets, not change the function.
So you can also change the functions. The functions are a little more baked into how JuMP works, for example, because when you write down a quadratic expression in JuMP, it will turn it into the quadratic function. But you're also free to define functions, and that might be the right way to, like for some solvers support piecewise linear functions. Should that be a function, or should you define a set which is the graph of this function?
But let's say at least for the first approximation, it's safer to do the sets. So the JuMP will be able to.
I think it's easier to model if you define new sets rather than new functions. Okay, so just a peek of the MOI API, not too complicated. We have what we call optimizer objects. So MathProgBase has solvers and models. We don't have that. MOI drops those two separate categories. The optimizer is basically both at the same time. And we call it optimizer because we don't, to avoid clashing with the name solver, we might have some packages that continue to support MathProgBase and MOI at the same time. So we don't want to have a name clash with Groby solver being the MOI version or the MathProgBase version. So that's one of the reasons we chose optimizer. So you create a OSQB optimizer, you add a variable to it, add variable returns the index of the variable, then you can go and add a constraint, and you can say that this single variable, the function of the constraint is a single variable, and the set is less than, and the set's parameterized by the bound. And that returns a constraint index, which you could then set and get attributes on. You can delete. You can use this constraint index to delete the constraint later on. That's what these functions return. Okay, mention this. It's important to know that the constraint index is parameterized by the function and the set. So that's another level of type safety. It returns an index, and that basically it's if it could just return an integer, then it would be easy to confuse, well, what is this integer? This type parameters say that if it returns a, the type encodes what type of constraint it's referring to, which means that later on, when you use this constraint index, you don't need to say this was an index into a single variable less than constraint. That's all encoded in the type of what it returns. So as I mentioned, you can delete variables. We have a function called isValid to check if an index is valid. So if you've just created these indices, they should be valid. Then you can delete them from the model, and then they won't be valid after that. So this is pretty simple, but this has been missing from JuMP for quite a while. The same thing, similar thing at the JuMP level. What you do is you create a JuMP model. You say the optimizer, for example, can be Gurobi optimizer. You create a variable, so this is exactly what you would do before, but now what's happening is that JuMP will create a single variable less than constraint when you put a bound there on creating the variable. Again, linear constraints is exactly the same as before, but what will happen is that JuMP will turn this into a scalar affine function and a greater than set. Second order cones change. JuMP 0.18 has a norm syntax for second order cones. That was kind of finicky because you had to write the norm in a very particular way, and it wasn't very composable. To make things very clear, right now the way to model second order cones is to just say that this vector of variables belongs to the second order cone. That's it. We might clean this up a bit. We may be, so for example, JuMP could recognize, the dimension of this. We don't need to force the user to write that down. That's not implemented yet, but that would be an easy thing to do. Another hypothetical constraint is this would be a vector affine function, x and 1 minus x belongs in the complement set, and that's one way that's used to represent actually an integrality constraint on x if you're in the complementarity world. So we haven't defined the complement set, but if you did, could look like that. So this is what using MOI and JuMP looks like. Constraint returns a reference, so we make a distinction between a reference and an index. An index is an integer with some type safety wrapped around it. A reference actually lets you be able to point back to the original object. So we store also the model that was attached, the model that this constraint belongs to. So you can go from the constraint reference back to the model. You can't go from, and if you're in the MOI world, you cannot go from the index back to the model. So when you create a constraint, it will return a constraint ref, similar to what JuMP does now, but now the constraint ref will be parameterized by the type of MOI constraint. So this index will be exactly a MOI index. There's nothing else there. Yes?
What if you have defined a generic constraint that appears in different formulation?
The way our model of that has not changed, but hasn't changed. So the constraints are tied to models. They don't float around and belong to different models. Just like the variables are tied to models, they can't really float around. So the way we deal with that hasn't changed into the new JuMP. Yep.
That second order cone constraint is, so you can also write the rotated second order cone in that form.
Yes, so we have a set for the rotated second order cone. That's a different set. Okay, so this has come up already. There's a very natural question once you define this pretty generic interface. That gives you multiple ways to write down the same constraint. And so if you're implementing a wrapper for a MathOptInterface wrapper for a solver, which sets should you support? Which types of constraints should you support? And this really boils down to who should do the work of transforming the problem. I don't think there's really no good answer to this. There's no very general and good answer to this. So we don't have one. What I would say is that MOI leaves it open for that balance to be discovered. Maybe we can find an equilibrium. How many users complain? How much work does the solver author want to do? The interface is designed to let you find that equilibrium and decide which types of constraint do you want to support, or do you want to tell your user you have to use these sets because I don't want to deal with transformations. So a few common situations, we allow you to define the vector find function in the 0 set. That's a multi-dimensional set. We also allow you to write multiple scalar find functions in the equals set. Mathematically, that's entirely equivalent. We've decided so far that the scalar find function in equals to, if you're working with an LP solver or a solver that has an LP-like interface, that's the much more natural interface. When you look at the APIs that LP solvers have, their interface is always constraint-wise, so you have row-wise, and you might have bounds on the rows. So we say that for example, the Groby interface that we've implemented takes constraints in the scalar find function in equal to rather than vector find function. Users could write this down and we'll reject that, saying we don't like this constraint, or not that we don't like it, we don't support it. We didn't want to go through the effort of.
I think it's issued.
Is it implemented?
I think so.
Oh, if it's good, then someone did want to go through the effort of that. It's also a progressive thing, so as you can start off by supporting the ones that are more naturally mapped to the solver API, and you might want to support more afterwards.
The solver package responsibility to implement.
Yeah, so JuMP does not do these transformations, and MOI does not do these transformations. You could think of a library that sits in between in between MOI and the solver that does the transformation. So that's related to the bridges that Benoit is going to talk about tomorrow. We also define a geometric mean cone, which Ulf showed us how to model using both power cones and second order cones. If you are wrapping mosic.jl, should you support the geometric mean cone, or should you tell your users to use the power cone or the second order cone? Our answer is it depends on how much work you want to do. We have to keep things flexible because we're a distributed group of people. Everyone works on the pieces that they want to work on. So this framework lets you find that balance. Okay, attributes are another new thing in MOI. Pretty straightforward. You get a variable index back, constraint index back. Once you have those, okay, so you can set attributes on the model itself. So for example, the objective sense is an attribute of the model, or this object returned by the optimizer. So the model is an optimizer. We kind of use those two words interchangeably now. So the objective sense is an attribute. The objective function is an attribute. You would provide scalar or find function if you want. Then you can set attributes on the variable. So you could define the variable primal start, which is this initial starting point for this variable. On that constraint, you could provide the constraint dual start. That's another attribute that we define. Yeah.
Question: do you imagine sometimes some attributes can help the solver add the variable properly in his model? So do we imagine adding some attributes to add variable?
Like which attributes?
Annotation attributes. Or when you decompose.
Yes, I'm hesitant to. change the API.
When
Yeah.
when is the model built?
Which model?
When does the internal solver get the variable?
That depends on the wrapper. So what you could do is let the user create variables, let them set attributes, and then pass that down, cache those, and call the lower level API after you have those attributes.
So the solver just needs to have the model created before you call solve, or like when you call solve, you could build the model there. If the Julia interface wants to do that, you can do that.
Yes. So I'll talk in a little bit about we have different ways to build the model and the way that works in JuMP. So I'll talk about that in a little bit. So this is if you're using the MOI API directly. If you're using JuMP, it should be mostly a one-to-one mapping. We haven't entirely tidied this up yet, but here's a little tricky point. What you can do is create a JuMP model, add a variable to the model. We still support this syntax for creating variable bounds, so bounds on variables. So once you've added a variable with a bound, you can then ask the JuMP model for the reference to that constraint that represents the bound on the variable. And then once you've pulled out that constraint, pulled out that reference, you can set MOI properties on it. So a little tricky here, we're overloading the API. This is a reference, JuMP reference, not a MOI index. And this is a JuMP model, not a MOI model. So that means there's one level in between here that translates this call on a JuMP model and a JuMP reference to a call on a MOI model and MOI reference. Not very tricky.
So as you intend to put everything into JuMP in the end? I mean,
So we can imagine a nicer syntax for this.
if you say constraints equal 10, that should do.
What do you mean?
The constraints.
Can you say that again?
You say the constraints reference, you assign it a value. That's the value of the constraint, the real value.
What do you mean the value of the constraint?
Right-hand side
Right.
equals 10.
Yeah.
Right. So that bound ref is now recognizes the bound as a constraint.
Oh,
Yeah, but we need some syntax which is straightforward. To the same way that you can assign a value to a variable, you should be able to assign a value in the JuMP modeling language without having to know anything about the MI syntax.
yes. So I mean, you can set. So for example, this is just JuMP syntax. This is what you can do right now. I'm showing the way JuMP is meant to be relatively transparent in the connection between JuMP and MOI. Hopefully, the intention is for JuMP to be a nice syntax on top of MOI. So if you understand MOI, great, you have access to all of this, and this is easy. If you don't understand MOI, you should still be able to do this. We haven't put a little nicer syntax on this yet.
You could
Yeah.
also add the bound constraint separately to the variable macro, and then you have the constraint reference. That would be
Yes. So you can also you can add at constraint x in greater than set, and then that would return a constraint reference. That's a little awkward way at the JuMP level to do bound constraints because we've been supporting the syntax for a long time, so we're not going to get rid of putting bounds there.
We say we want to bound the real value of the constraints
What do you mean bound the dual value?
at cuts to the dual product. For instance.
Okay.
You might want to do that to standardize so you can box the dual. If you have a good estimation of what the dual value should be, you
Yep.
can find boxing. And so you would like to use exactly the same structure that you have used for variables, like you would say add constraints, add constraint C, greater or equal to.
Okay. We don't do that in JuMP right now. What you could do is, JuMP has infrastructure for building up expressions on variables. That is templated over the type of the variable, so if you want the type of the variable to be a constraint reference rather than a variable reference, that's relatively easy to do. So it'd be a little bit of hacking, but on the order of tens of lines rather than thousands of lines.
But I guess it's so you're saying like I have a model and I'm adding a constraint on the this primal and I'm adding constraints on the dual. That is not a mathematical programming problem. But a solver could have that information of like, I want you when you're running bound the dual. You could use the function, create a new property which is bound on the dual. And
Yeah, so
you could give that information and the solver will know to do whatever it is.
The idea of this MI is that it should hold information that can be useful for any of the solvers that are behind. It's not because
No,
syntax of Gurobi are not exploiting this, other solver.
You could create it, as Juan Pablo was saying, if it's just bounds on the dual variables, you could create a new attribute saying constraint dual upper bound, and if you recognize that in the solver that you've implemented, then the user is free to write down those constraints. If someone adds that attribute and tries to call a solver that doesn't recognize it, then they'll get an error. Yep.
You mentioned that there is a JuMP model and an MOI model.
Yes.
So why was there a need to do this duplication?
So I will show more about the connection between the JuMP model and the MOI model. Basically, MOI is an API. There's no operator overloading. There's no macros. It's just an API. And what the JuMP gives you is the nice syntax. That's the main difference. Okay, so just give into a peek of, again, the connection between the JuMP model and the MOI model. So JuMP variables, we've renamed JuMP variable to JuMP variable ref to be consistent with constraint refs. And the variable ref contains a pointer to the model, and it contains the MOI index of the variable. And the way that we implement this function, so I said that this function does a little step to translate between JuMP and MOI. Here's the exact translation. What we do is we take our model, we take a variable ref, then we call MOI on a field of the JuMP model called the MOI backend, and we extract we convert the variable ref into an index, and this is the full implementation. This is everything that's happening between JuMP and MOI. So it's one line of code. And also, for example, start values. We have a little nicer syntax for start values, and the way that it works, if you want to ask for the start value, you provide a variable ref. We can give you the start value, and this is exactly the implementation. It pulls out the variable primal start. And if you set a start value, it sets the variable primal start. So that's exactly everything that's happening between the JuMP level and the MOI level. Yep.
So these getters and setters, what is the compressive? Constant type or some other?
It depends on the MOI backend and how they choose to implement. So the solver wrappers are the ones that are implementing these getters and setters.
It doesn't depend on the indexes, for example? Like the way you're doing indexing now is not just linear. So does that affect the complexity?
Oh, you mean the solvers need to know if you've deleted variables or something like that?
Yeah.
That's again up to the implementation. So some solvers, if their natural API doesn't allow you to delete variables, like CBC, for example, the C API doesn't let you delete variables, so that's not implemented in the MOI wrapper. We have a layer in between that as kind of a buffer between the solvers that only support a really small subset and everything that you might want to model. And I'll get into that. I'll mention that later. We have, yeah, so usually the way to deal with deleted variables is just to keep a dictionary around and index into from the index from the user provided index to the actual index, that's usually a constant time operation. Okay, so that's some of the API. Status codes is another big thing that we changed. It's entirely different. The questions that we're trying to answer, the information that we provide in the status codes, you can basically break it into 3 questions. Why did the solver stop? So we have an attribute called termination status, which is intended to answer why did the solver stop running. It was running an algorithm. What was the thing that caused it to stop? Does the solver have vectors to return? Sometimes it does, sometimes it doesn't, and that's available in the result count attribute. And what do those result vectors mean? That would be in primal status or dual status. So best way to figure out what this means in practice is to go through a few examples. So let's say you have a convex primal dual solver, call it an LP solver, and then your LP solver has proved optimality, obviously within numerical tolerances or the gap that you've provided. So you solve an LP, solver is happy, it returns success, it has a solution, has a result to return, and has both a primal and dual feasible solution to return back to you. And the important point here is that none of these attributes said optimal. There's nothing here that said there's no optimal here. This is a bit tricky because Carlton, I was having a chat with Carlton, I think 2 years ago, and he was complaining about JuMP's optimal status. For example, IPOpt returns optimal. What does that mean? It's easy to misinterpret that as global optimality. And not all solvers, when they currently return optimal, that doesn't mean global optimality. And that doesn't, for example, with IPOpt, local solvers doesn't even mean local optimality. It might have just converged to a saddle point. And so that information, we decided to remove that misleading part and say success. And you have to know that if you're using an LP solver and it says success, then obviously it just found and it says success and it returns a primal dual solution, then you have to know that this means that it's optimal. Yes?
I don't understand the meaning of result count.
Yeah.
Okay. So the result, that's a little tricky. The result, a primal and dual pair is one result. And if you have a solver that wants to return multiple feasible solutions, then that would go too. Normally, this is one. While we were setting on this, let's design it so that the solver could return multiple solutions. But typically, I don't think we have any solvers hooked up that do that yet. So let's say we've proved we've proved that the problem is primal and feasible. If we're using a simplex-based LP solver, it'll say success. It'll return an error. I think we have an open issue to change this to not available or instead of an error. That might change. But what's interesting is the dual status will say that it's an infeasibility certificate. So you just solved it. You have to check was it successful, and then you look at the primal and dual status to interpret what you got back. I have a slide on that. Okay, so this is not too hard. All the esoteric error cases are where things get interesting. What if you're using an LP solver and it's trying really hard, and it gives up, but it knows that if you multiply the tolerances by 10, then you're optimal. And a lot of solvers, that's a pretty typical thing to do in solvers. When things get hard, check if you've solved the problem to a relaxed tolerance, and if you have, then just stop there. So we encode this as an almost success. That's how we encode this. And then primal status and dual status can change. It depends on which tolerances are satisfied. If you had to relax the primal feasibility tolerance, then the solver should say that I have an almost feasible point. And same thing for the dual. So this depends on the solver deciding which tolerances did it have to relax. Let's say the solver just stalls and knows that it's not even close to the solution. Then we return a termination status called slow progress, and it's up to the solver to decide it could stall with a solution, it could stall without a feasible solution, and we let you encode that information.
Sorry, primal dual solvers, so that's LP solvers and comic solvers?
Yes.
Not
It's,
NLP solvers.
convex, NLP, it depends. Yes.
So dual stat, so would you get a infeasibility certificate from IPOpt?
No, from IPOpt you would not get an infeasibility certificate. I have a different slide on that.
Oh.
Yeah. Yeah.
So regarding installing, if like C++, the code is running several methods in parallel, how do you have this slow progress status like that? You get this when the solver stopped, not if it's in the middle of the algorithm. So you called solve and it finished, and the solver decided to stop. If it's running multiple things in parallel and one of them stalls and it switches to something else, you wouldn't see that because it's just the solver running. This is what you get when it finishes. Okay, so MIP solvers also get interesting. If let's say you've proved optimality within the user-provided gap, then the result count would be 1. You get a feasible point back. That's how we say a MIP solver would return an optimal solution. Let's say a pretty common thing that MIP solvers like to do is that they've determined that the problem is either infeasible or unbounded. Almost all the solvers do this, so we have to have a way to report it. And then our termination status, since it's such a common thing, we have a special termination status called infeasible or unbounded. What if the solver has enumerated the branch and bound tree and decided that there are no solutions? In this case, there's no results to return, so we have a special status called infeasible, no results, that you've proven, somehow you've proven that that the problem is infeasible, but you have no results to return. If you time out and you have not found a feasible solution yet, then you get the timeout status and no results. If you time out with a feasible solution, you get 1 result, and hopefully it would be a feasible point. And then my favorite Cplex, optimal, infeasible. We would say solver says success. I would Cplex was happy to return the status, so I would call it a success. And then here, in the primal status, what you have is an infeasible point. This is exactly what the solver told us. It's success, and I have an infeasible point. That's how we would encode this. So for NLP solvers, let's say you've converged to a feasible point by some local gradient descent. We would call this success. By not just converge to a feasible point, converge to, let's say, IPOpt's convergence criteria. We would say success, and we would have both the primal and dual feasible point. IPOpt can also converge to infeasible points. Since it's converged, we'll say success, but it has an infeasible point here. And what happens with the dual, I'm not quite sure what you would get back if you asked for the dual in that case. Iteration limits, so we have a whole list of limits that you can specify. Iteration limit is one that we have, so if it stops with an iteration limit, that's to be the status, and you may or may not have, well, if you're iterating with IPOpt, you would always have the point that you stopped at, so it could return that, and it could say, is this feasible or infeasible, the current iteration. So that's how it would report that.
for invisible, you can also query the duals. It will converge to a point that
And what is the interpretation of that dual?
I'm not sure. The least invisible physical point.
What was the question?
So when IPOpt converges to an infeasible point, what do you get back in the dual?
I think it's the point minimizing the violation of the constraints.
If that point satisfies the dual feasibility criteria, then it should report feasible point. If it satisfies some other properties, but it's not dual feasible, then I would just say infeasible point. Or if it's a certificate of, if you can interpret it as a certificate of something, then you could say that, claim that it's a certificate. Yeah.
So on your previous slide, the MILP slide, there is this, so I don't know if many have observed, so Cplex, when the JuMP keeps throwing this error called Cplex 3003 error.
I don't know what that is.
So whenever I run this continuous program, it keeps showing it's not a mixed integer problem. Is that something which is addressed because of this?
I think that's a bug in the wrapper.
Objective bound on an LP, and so after the solve, JuMP just goes through saying, can you tell me the objective value? Can you tell me the bound?
And then it thinks it is the same.
And it only allows some attributes to be queried depending on what type of control. And so it's just a bug in the
I see. So it's not to do much with this optimal node. Okay.
Yes.
Well, not really a bug. It's like it's JuMP not knowing.
It's a design issue with JuMP not knowing if it has the ability to query the lower bound.
Lower bound, I see.
Yeah, that is addressed by the attribute, by the redesign of attributes. Yeah.
Sorry. So I remember on the documentation for conic and LPs, which was saying, you defined the notion of duality quite clearly. But for NLPs, I haven't seen that in the documentation. Is it planned to be defined clearly what the duals are?
We haven't written that down.
Is it decided like what that notion will be?
So we try to have a convention on the signs of the duals at least, because different solvers might decide to use duals with different signs. Once you fix that, then I think the rest is pretty standard Lagrangian duality. Yeah.
Okay, you go to the next slide. So
Sorry.
if you had if you get a success for an NLP solver, you get success, result count 1, primal status, feasible point, dual status, error. There will be, trust me, I'm optimal, but I cannot prove it to you.
I mean, it could be a local solver that doesn't keep a dual solution.
No, but it's just like if you knew that it was IPOpt, that it's like you want to trust the solver that it's a local, that he claims that it's an optimal solution, then you need to know what solver it is.
Yeah,
And
so
that will be
the definition very much depends on the solver. You need to know
the success.
what is success. What are the properties of the set of points to which a solver can converge? You have to know that if you're using the solver.
But it's also like if you do get primal status and dual status, both feasible points, then if you understand what duality was, you can pick those solutions and you can confirm yourself that indeed it was optimal.
Yes. Yes. So usually with the duals, you could use these to check if the solver is telling the truth. Yep. Okay, so that was statuses. Constraint modifications. I'll go through this quickly. There's a few different ways to modify things. You can, let's say you have a constraint x less than or equal to 1. You want to change that to x less than or equal to 2. One way to that is to replace the constraint set with another one of the identical type with a different parameter, since the upper bound is a field of the less than set. So we have a constraint set attribute that lets you, given a constraint, let's replace the constraint with another one of the same type with possibly different values for the fields. If the set in the constraint changes, then it's a little tricky because the set is encoded into the reference object, into the index object. So you cannot continue to use the same index. So we have a function called moi.transform, or you could replace the constraint with you can replace the set with a new set, and it will invalidate the old index and give you a new index. That's fine for simple things. We can also have, if you're replacing one coefficient in a big linear expression, you don't want to create a whole new linear expression and replace it. We have a way to modify. We have a list of ways that we allow you to modify, for example, scalar affine functions, and you can make a scalar coefficient change to one function, and that should be, if it's implemented correctly, it should be a constant time operation, rather than having to do a whole operation on all the terms of the function. Yep.
The second line. So when you say we issue a new index, you mean index for the set constraints or for the variable?
Set for the constraint. So if you change this function or the set, since the index type is parameterized by the function in the set, you can't use the same index that you had before. So it returns a new index that's parameterized by the new, if the set function, yep.
So if it's somewhere in the tree and you want to keep these constraints, the upper bound constraints alive in one subtree, then you have invalidated it?
That depends. You could, so infinity is a valid upper bound. It's up to the solver to decide if it actually wants to throw an error on that or not. Or you could transfer, like if this is a variable bound if this is a variable bound, just delete it, because variable bounds are efficient anyway. Don't worry about deleting a variable bound and adding a new variable bound is perfectly fine. So modifications, you can always step around this by deleting the old constraint and adding a new constraint. And if it's a variable bound, just do that, it's fine. If it's a big linear row that you want to turn off for now and then bring back later,
There is some questions
yeah.
to the utility. It's like, what's the minimum set of things you want to keep in MOI?
Yeah, I mean, you can. It depends on the solver how efficient it would be to delete that and then add it back later. Given that you're going to basically all these constraints, the goal of these modifications is to have the overhead of these constraints be much less than solving the problem itself. But if you're going to deactivate a constraint, solve an LP, add a constraint again, when you're solving that LP, you have to at least do a linear pass through all the data. So I would question how much you would save by keeping the constraint around and setting its bound to infinity versus deleting and then adding it back later. It depends.
Just the constraints might be alive in our own data structure. And then, so if the MOI has deleted the constraints at the bound, then good.
So I guess you can say this has not changed between MathProg base and MOI. So MathProg base, I think you could set infinity as an upper bound, and solvers may or may not complain if there's a row that has no lower bound and no upper bound. It's a question of who wants to do the work of keeping track of that.
Is there a limited set of functions that JuMP or MOI supports, or can I define my own function and then associate some attribute with this function is complex, for example? No, I cannot give you the exact form of the function, but I can guarantee you that it's complex.
You can, the list that I showed, this single variable, vector variables, affine functions, and quadratic functions, that was currently exhaustive, but you can define, the interface lets you define a new function. Whether it's immediately easy to write that down in JuMP is another question, but you can define that as a function. What you cannot do with these, this is not a graph of expressions. You can't, there's no data structure to represent composing this function with that function, so it's useful to know that this is convex. That's not what we do here.
What if the function has no closed block? I can only read it to you as a function call.
In principle, that's fine, but we haven't done any work on that.
It's originally the same NLP interface that is currently there.
Yep.
So you can mix and match the NLP interface with the conic interface, and in theory, Nitro could pick that and use both.
And convex is not defined in any way as an attribute, for example?
No.
So does the scalar coefficient change work on nonlinear constructions?
No. These are only for MOI function. I think for this linear, affine or quadratic constraints.
Or quadratic?
Yeah.
So if I have log of ATX,
No. That goes through the nonlinear.
you have to expand.
Yeah.
There's the trick. You write the affine constraint you can write down the affine part in vector format. Then you could use this and then add another constraint that just does the X of this new
Or the new one.
And that's it. Yeah. So you can do that now, and you'll be able to do it.
Okay, so MOI, we've released 0.4 this week. There's been, if you haven't used it yet, there's been a whole lot of work on it. We started at last year's workshop. There's over 700 commits, and I was surprised to see 400 issues have already been, the issue count is above 400, and maybe there are maybe 30 something open issues. So we've gone through a lot of work to make this into a nice interface. In terms of which solver, so the next version of JuMP 0.19 will not support MathProg base. It will not be able to communicate with solvers that implement MathProg base, only with MOI. What we have done so far, I'll separate it into a few categories. We have some solver wrappers that are already released, as in the Julia version is tagged. You can get it by package add. These packages, except for MoSec, the MOI wrappers are all in the same package, same as MathProg base. In the case of MoSec, it's in a separate package. These are all tagged, and you should just be able to pkg.add them and get the MOI version. The second category of solvers, we have MOI support either in a pull request or it's in the master branch, but it hasn't been released yet. So these are in pretty good shape, but just need a few things left before we release them. And then the up for grabs, basically, if you start working on these today, you don't have to worry about conflicting work because nobody's gotten to them yet. That's what I mean by up for grabs. We do have, if you start digging through these wrappers, you'll see two packages called semi-definite opt-interface and lin-quad opt-interface. These are basically helper APIs, given that Groby, Cplex, Express have such common C APIs. These are helper APIs that wrap these a common subset of these APIs and implement MOI. So these were implemented to accelerate the MOI wrapping process. It's entirely, if you're writing a new wrapper for a new solver, it's entirely optional if you would want to go through these helpers or if you just want to implement the interface directly. Any questions about MOI wrappers? Yep.
You mentioned except for MoSec, they live in MOI?
They live in the, so ecos, the wrapper is ecos.jl. So ecos.jl has the wrapper for the C interface to Ecos, the MathProg base wrapper, and the MathOptInterface wrapper all in that package.
And MOSEC.
MOSEC has a separate package called MathOptInterface MOSEC that has that wrapping code.
So in that case, so to add a second order Coney constraint, for instance, for MOSEC,
Yeah.
can I still use that format of the MOI constraint you had, or is it specifically from the MOI MOSEC?
No, MOSEC supports the standard most of the standard constraints we've defined. That second order cone is one of them.
Is one of them.
Yeah.
Because in the test examples of MOSEC, they look very weird in their constraints are MOSEC.js. I don't know if you have.
You can ask Wolf.
Sorry.
I'll probably talk to you later.
He doesn't want to talk to you anymore. Weird.
Yeah.
Is this like intended to be a teaser for CPEX people? Or how can you find this new release with a CPEX version?
I'm just reporting on the state of the wrappers. These are driven by, I mean, except for MOSEC and potentially Artelis, these are driven by people who want to use these solvers from JuMP. And I mean, Cplex, I imagine, will happen pretty quickly because there are a lot of people using it. I don't know, Oscar, if you...
I originally started writing the CPEX wrapper, and then because we started writing Gurobi and GLPK and they're all the same, then we ended up writing the other linquad thing, and then I haven't come back.
I would expect that to happen pretty quickly, but it's all written by people who want to use the
So
solvers.
like release version is the current release version, not the final release of MOI.
No, this is as of today. This is not as of the point in the future when we release JuMP 0.19.
But let's say you're going to start playing with MOI now, you won't be able to use it. But it shouldn't make a big difference. Whatever, if you've got a solver that uses Gurobi, it should also be able to use CPlex once it's released.
So if we go back to the activity of your group, you can see that during the winter you are quite slow, so we're going to get to running there in this setup once we had that.
So the reason for the winter activity is that because we have split the test package in a different way.
Oh yeah.
So this is not all of the commits.
So there's a lot of commits missed here because originally we had MOI split into 3 different packages, and around this time we merged them into one.
Yeah, you should involve people from Chile or
Chris?
Callbacks. So does the linquad interface, does that have anything to do with callbacks? Or is it
No.
It's going to be totally solver specific. So they work in Gurobi using a Gurobi.set callback.
So have you looked at Cplex? Because they have
No.
more advanced callbacks there. Have you learned anything from Gurobi that would be helpful for
No.
Cplex?
Haven't looked at that at all.
Okay, so that was mostly on MOI itself. I gave a little peek of how MOI talks with JuMP. On the JuMP side specifically, I'll start out by saying what has not changed. It's a shorter list than what has changed. The macro syntax has not changed. Your variable constraint, NL constraint, expression, that has not changed. The only difference in being how we encode second order cone constraints with that norm syntax, we got rid of it and we have a different way to encode second order cone constraints. So I meant variable construction syntax, basically the same. I think we changed the SDP keyword to PSD for aesthetic preferences. That was basically it. Automatic differentiation has not changed. We reverse diff sparse was a separate Julia package that I wrote that JuMP was using for AD, it was not a sufficiently standalone package that I decided just to merge it into JuMP so it's easier to maintain. But the AD code otherwise has not changed. We did fix, when adding new tests for JuMP, I did come up with a bug and fix a bug that Abel found, but otherwise the AD has not changed. Okay, so what has changed? Containers, the objects that you get back when you create a set of variables, that has changed. Names, I'll go into what that means. The data structures for affine expression and quadratic expression, that has changed. That was a pretty significant change recently. How we interact with solvers, of course. Some software engineering improvements that I'll get to. And we also now use Documenter for the documentation and doc strings. We're kind of catching up with the Julia ecosystem in terms of the documentation infrastructure. So JuMP containers. If you've seen a JuMP dict before, every time you saw that, it's now going to be just a base Julia dict. If you never saw this before, don't worry, because it doesn't exist anymore. JuMP array has been completely rewritten, inspired by the access arrays package. And so when you're dealing with JuMP containers, you should know that there are 3 different things you can get back, and it depends on how the set of objects you wrote down are indexed. So if you create a variable, this is an anonymous variable, so there's no name there. If it's indexed by 2 dimensions, 1 to 5, 1 to 5, and these are always 1-based intervals, then we just return a Julia array of variables. To keep it simple, you can now use this array in linear algebra operations because it's just a plain Julia array. There's a little trick, I'll skip that one too. If one of your sets is, if we do not know that your set's based on compile time information, if we do not know that they're all 1-based intervals, then we return a JuMP array. So at compile time set 2, we only know that the set 2 would be an interval, a range, and the starting point of the range is not encoded in the type, so based on this we would return a JuMP array. Same thing if you're indexing over sets of symbolic values, you can use any sort of index set you like, and if it's basically if your index set is a Cartesian product, then we'll return a JuMP array. Finally, if your index set is not a Cartesian product, so if you want to index over the, you basically set I from 1 to 5, and then the second coordinate would be 1 to I, you can write that down and we will just return a dictionary index by those tuples of possible values. And same thing if you only want to index over the odd integers or if you want to filter out the possible indices, we would just return a dictionary.
What is the access type now?
Dictionary is constant time. It's the Julia built-in dictionary. And all this applies if you construct a block of constraints, a block of expressions, a block of nonlinear constraints. It's the exact same syntax and you get the same types out. On top of this, we've make it a bit more explicit that you can request a certain container type. So if you really want a JuMP array, you've designed the rest of your API to always work with JuMP arrays, and just in one situation, you happen to have something indexed by 1-based intervals, you can request a JuMP array. If you know that your sets are 1-based, you can say, I really want an array, and that will give you an error if the sets are not 1-based. So just a little more low-level control. What's happened with JuMP arrays, these have been rewritten and used to not be able to slice them. So in current version of JuMP, If you created a JuMP array and then tried to extract a slice of it, it would give you an error because the colon is not in the index set, and you can only index with things that are in the index set. In point 19, you can slice over JuMP arrays, and it will keep the meaning, the right axes back. So, for example, the dimension 1, your index set is ABC, dimension 2, XYZ. If you drop out the first dimension, so if you want to fix Z in the second dimension and get everything in the first dimension, you can, it'll return a JuMP array that lets you index using the same sets as before. Okay, names. JuMP has gone through a few iterations on how to deal with names. And now there are two different concepts. The first is we've introduced names for variables and constraints. We got by for a very long time with not allowing you to assign a string to name a variable. And then we decided, okay, it's actually useful for debugging okay, so that's not quite right. We have a name for the variable, but we don't communicate, in 0.18, we don't communicate that to solvers. You can't really look up variables by their string names. It's just used for printing purposes. What we now have string names in the way that you would expect, so you can assign a string name to a variable and a constraint. You can look up objects by their string name, and we can pass these to the solvers. So when Cplex is printing an error, it could print the name of the constraint. On top of that, we had this model level scope. So when you declare a variable x, like this x symbol goes into the model, and you can look up, in the model you can look up x, and x would be this two-dimensional object. So this is not this is not a name for these variables, it's a name for this two-dimensional object. So string names apply to scalar variables and scalar constraints. The model level scope is if you create a collection of variables or constraints, you can look up that object and get the whole collection back.
And that's the same.
Yes.
So you have the model, give me the object.
So if you wrote down model and look up x in there, you get.
X is the x you added in the macro.
Yeah. And this is, you need to know about this when writing JuMP models, because if you create, JuMP will complain if you create multiple variables with the same symbolic name.
What if I create an anonymous variable?
Anonymous is fine.
And then, but then
You can't look it up.
variable doesn't have
Right. Right.
model.
So I believe Carlton uses this in power models when you're constructing. You have lots of different functions that construct blocks of objects and constraints, and you want to look them up later. This is a convenient way to get back blocks of constraints. Yep.
So say you have two blocks of constraints, variables x and y, and you want to define attributes for one of those two blocks. So you want to say y a binary variable. You have to go through all these variables, or you can set attributes on the vector itself.
So Julia has a broadcast syntax that actually makes that automatic. If you put a dot between the function name and the open parentheses, it will broadcast the operation over all the elements of your collection.
And that works over all the containers in JuMP.
Yes. The reason why why the current version of JuMP doesn't work on 0.7 yet is because they rewrote the broadcast infrastructure, and we haven't updated JuMP arrays for the new broadcast infrastructure. So that's it's a hairier part to implement, but it looks pretty nice when you use it.
I guess that one, the model scope, I guess is something that so I kind of asked about, is suppose they have three models that have their copies, or very similar, but have the same set of variables. And if they'd like to actually add things to X variable to model 1, they could do model 1 X, then I will get the object with the X variables for that model.
Yes. Yep. Okay, so affine expression and quad expression, we've redefined how these work in JuMP. Previously, starting off JuMP 0.1, we've defined an affine expression with a vector of variables, a vector of coefficients, and then a constant. This is what we've done forever. And when we were adding things, we just, like adding two expressions, you concatenate the vectors, and we worried about, we eliminate duplicates in one pass right before we send them to the solver. That's what we've been doing forever. Same thing for quadratic expressions. We would just have a list of quadratic terms and an affine part of the expression. I did some benchmarking. So the issue with these is they're a little unfriendly to work with if you're designing a JuMP extension that the user gives you an expression, you have to manipulate it and do something to it. It's a little annoying to deal with the fact that these could have duplicates that affects everyone who uses these expressions. So that's a bit annoying. In 0.19, we did some benchmarking and found out that it was actually just a little bit faster if you replace these vectors, these list of terms with a dictionary just from the variable to the coefficient, and this means that there's no duplication of, this eliminates duplicates when you add terms. It's a little bit faster, and then there's no pass later on to eliminate the duplicates. So this involves going through and changing every single piece of code where JuMP interacted with these expressions, and if you're writing an extension that deals with these objects, you'll have to update to this change, but overall it should be easier to deal with. We use an ordered dictionary so that when you iterate through these expressions, you get the answer is deterministic. So Julia's base dictionary has no ordering, and if you run the same thing a few times, you could get, if you loop through all the elements in the dictionary, you can get something different. You can get a different order back. We thought that would be kind of annoying in JuMP, especially if you're walking through this expression and constructing a mathematical model based on the terms in this expression. We want that process to be deterministic, so we use an ordered dictionary. There's a bit of a performance penalty for doing that, but I think it's worth it. Okay, so JuMP has a multi-backend problem, as Jared likes to call it. We support a lot of different things, and not all the solvers support all the possible things that you can do with MOI. So modifications, for example, some solvers, the API just does not let you change coefficients. What do? Our goal here is that in the cases where the solver lets you make efficient modifications, we want that case to be efficient, and if the solver doesn't, then we want the option to still make that modification because it's nice for modeling, and we also want to make it clear when was this fast and when was this slow, because it's easy to write an algorithm where you think that modifying the coefficients is fast, but actually it turns out to be the bottleneck because we had to imitate modifying the coefficients because the solver actually doesn't do that.
I think you're good, Jared, man.
Yeah. So the way we deal with this, this is a tricky problem. I don't think other modeling languages have a good situation that lets you make. I should be careful since Stefan is here, and I would say it's not objectionable to say that this is a pretty tricky problem to let you have these operations be fast when the underlying solver supports it, and provide a reasonable fallback when it doesn't. The way we deal with this is we now store the problem data only in MOI format. Previously, JuMP had an extra copy of the problem data. For example, the linear constraints would be a vector of linear constraint objects at the JuMP level. We've thrown that out, and now the only place where JuMP stores problem data is in the MOI backend object. So that has a few implications. When we add a constraint, this is our definition of add constraint. We really just call MOI add constraint on our backend, pass in the object information, set the name maybe, and return the reference. So we do not store an extra copy at the JuMP level. So then we have a few different ways of communicating with solvers. We settled on 3 different modes in which you can run JuMP. I call it direct, manual, and automatic. You'll see why manual and automatic make sense. Direct is when this MOI backend could just be the Gurobi model object. Nothing in between. It's really JuMP attached to the Gurobi model. Any change you make goes straight to Gurobi, and if Gurobi doesn't like your change, you'll get an error, done. And there's no extra copy of the problem. This is something you could not do previously. You would always have a copy in the JuMP level. This direct mode lets you remove that copy of the model. So this removes a copy of the model, makes it very clear. You know exactly what's happening, or if you know the Gurobi wrapper, you know what's happening. And you'll get an error if you try to do something that the solver doesn't support. We will be using this mode for callbacks because we have, this makes it very clear what's the relationship between a Gurobi variable and a JuMP variable. You need to do that mapping when you implement callbacks. So to use callbacks, our plan is if you're using callbacks, you should be running JuMP in direct mode, and then we'll have an interface for callbacks with that. It's as if you were using the Gurobi Python interface, the Express Python interface, but in Julia. The manual mode, so this is going from lower level to upper level. Most people will use automatic. The manual mode is when our backend is what we call a caching optimizer. So this caching optimizer is an object we've implemented that will accept changes that you make and cache them. And basically, you can build up a problem without having any solver available. Just give it to the caching optimizer, and then at one point you can attach the solver, copy everything into the solver. And if you run the backend in manual mode, it's as if any changes that you make will be instantly copied to the solver. So you basically engage the clutch. Anything you make, any changes you make go straight to the solver, and so we say the solver is attached. In automatic mode, we again have this caching optimizer, and it will let you make changes. You can add constraints, you can delete constraints, you can use the full interface, and we will silently dump the solver and create a new one when we need to. And again, so this is what most people will use and what is a nicer interface. But we've had requests like, you're using JuMP. How do I know if my incremental modifications are being passed to the solver? We can now answer this and say, if you're running direct mode, yes, it's efficient. It's as if you're talking to the solver directly. Manual mode still lets you access changes, but you can tell the caching optimizer, okay, I'm about to make changes. Dump the solver, forget the solver, I'm about to make changes, and then reload it later. So it provides you a nice interface. So you don't have to reconstruct the problem from scratch. You can just make modifications. And in automatic, maybe it's not clear. We don't. It depends on if the solver supports it, but you won't get any warnings if it supports it or doesn't. Yep.
About caching, I expected that your native mode would see when it's better to cache some information rather than transferring the comments directly to the solver.
So we do not do that. So the caching layer, it's either transfers everything or collects changes and sends them all or does them all at the same time.
So essentially, it's like you want to modify the model. If you can modify the model directly, it will do it. If not, it'll recreate the model to.
Yes. So if you modify one coefficient, it will
It's
direct.
not so
Yeah.
drastic as that. I have something in mind which is much
Yeah.
more key. So if you add variables, say within the loop, you can add them one at a time and call the solver each time, or store them in a temporary vector and add a vector variable at once.
Yes. So that decision should be made in the solver wrapper layer. So like the CBC or the Groby, the Express MOI wrapper can decide, I know that Express is slow at adding variables one by one, so I'm going to cache them.
Yeah, but the function that is called doesn't know that you are going to call it again and again in the next few iterations. So.
Well, I mean, if caching optimizer doesn't know that either.
Yeah, so I mean, maybe some automatic mode, maybe some intelligence if you call it twice at the rows.
Yeah, intelligence is hard to, I mean, we try to minimize the intelligence in the code. It lowers the burden on us.
But I guess you said the direct is really direct to the Julia interface.
So yeah, so this is direct
That could be
to
intelligent.
the Julia interface, where you actually know that this is Groby. I know that if I wanted to do column generation, I want to add the variable with its coefficients at the same time instead of adding a variable and then setting coefficients. That is something that we would say should happen in the Groby wrapper.
Or do you have separate function to do this? Or?
We do not have a separate function.
But you do have solve. So
Yes.
When Groby receives, so Groby knows that it should cache everything and only build things when it gets solved, it could do that.
Yes.
And it could decide to do that in some intelligent fashion.
Okay, so that's incremental modifications. Software engineering improvements. So I now work at Google. I learned a few software engineering tricks.
You mean the training was not that good at
They don't really teach that at MIT. One of the things that I'm very happy about is that JuMP's unit tests do not depend on having a solver available. It's nice, especially for MOI when we are in a state of flux with which solvers actually are implementing the interface. I can work on JuMP and set up JuMP to work without caring about the current state of glpk.jl. It's also nice because when in testing the current JuMP 0.18, sometimes a solver might return a little weird answer, and that causes JuMP's tests to fail. And it's really not what we're meant to be testing in JuMP. We define a very clear API. We should be able to test that every single component works, and we can do that without using a solver. So this makes development simple when we're not held up when a solver breaks. And the way we test is JuMP actually working when it talks to a solver. We have some mock solvers that implement the MOI interface and return dummy solutions to test that can JuMP communicate with the solver. Yes, but we use a fake solver to test that rather than a real solver. Let's see. On top of this, we have a little lightweight text format for constructing MOI problems, really just for testing. I know it could be taken overboard, it could be taken a little too far, but we do allow you, have a little compact way to define MOI instances, and this is a little text-based language that's defined in MOI. So when you're writing a test, I want to check that I want to create this instance. You can write it in a pretty compact way. It is not extensible. It's not meant to be extensible. It's meant so that we can test MOI and JuMP. But what I can do is write this little string, load it into an MOI model, and then basically create a JuMP model and test that the JuMP model equals this MOI model. And this is how we check that JuMP created the right model.
So you created a mini language because it kills two birds with one stone.
Yes, but I'm not going to call this a modeling language.
I don't think Chris
it's
is saying it's for anybody else to use either.
It's a little parser. It's finicky on the syntax. It's not meant to be user-facing, but it's really a big improvement for. I can read this test. I can look at this, look at the JuMP model, look at this test. I can validate that this is checking the correct thing, and then run that test. So this is good for develop. It's also useful. We use this in some of the tests of the solvers. We have a suite of tests implemented at the MOI level. Does the solver solve this instance correctly and report everything as we expect? And in some of those cases, we can write that problem in this form. So if you look at the test, you'll see some problems written down like that. Hopefully, it's pretty clear what's going on there. And this eliminates a lot of cases. Well, I need to use JuMP to test my solver. We want to avoid that. It's too much of a circular dependency. Hopefully the solvers should be testable without using JuMP. The exception is with nonlinear. JuMP does a lot on the automatic differentiation side. This little language doesn't support nonlinear, but for everything except nonlinear, you can test solvers pretty effectively without needing to depend on JuMP. We're working on, if you look at the documentation, we have a lot of empty documentation, but the sections are laid out. We'd like to have a style guide on how do you actually write models in JuMP and Julia. What are the naming conventions? How should you format things? A lot of these questions are pretty important once you start proposing JuMP to be used in industry. You say, here's JuMP, and someone sees JuMP. Well, how do I... if you're working with a group of developers, you need a uniform way of writing things down. So we'd like to have a style guide. If you have ideas, come talk to us. And also design principles for composing, building extensions around JuMP. We want to provide some guidance for people who would like to do this. What is not yet done, so JuMP 0.19 is not released yet. The major blockers for this, we don't have model printing set up, not there yet. Tidy up the API, so there are some places where you need to use the MOI version of things. We don't have a nice JuMP version, for example, modification, setting the solver. We intend to tidy that up. Documentation, as I mentioned, is missing. Callbacks, Oscar has an example, but we'd like to get a working example before we release the next version of JuMP.
JuMP callbacks or
Callbacks with Gurobi. Yeah, Gurobi and with a JuMP model, yep. And we will definitely be supporting 0.7 before the release. What else? In terms of maintaining the JuMP MathProg base, we would like to release a version of JuMP 0.18 that supports Julia 0.7. That hasn't happened yet, but we're making progress. So we won't be, we don't intend to block people from updating to Julia 0.7. You can choose when you want to update the JuMP version and the Julia version. And as I mentioned, the MathProg base and the MOI wrappers will be coexisting for a while. Just wrapping up, say a few words about yesterday's announcement that Juan Pablo made. JuMP is joining NumFocus as a sponsored project. What that means, so, and on top of that, we're moving away from the JuliOpt brand and moving towards the JuMP brand. So what that means in terms of what that means in terms of NumFocus, NumFocus is a nonprofit organization. That means that they can facilitate us receiving donations if anyone would like to donate to JuMP. I'm not asking, I'm saying that if that situation occurs, NumFocus provides the infrastructure for that. Also for receiving grants, if you're not part of a university or if you don't want to tie the funds to a university, or if the university overhead is too large, NumFocus is a mechanism for receiving grants. They help sponsor Google Summer of Code. They could potentially hold funds for the JuMP-dev workshop. If JuMP-dev moves around year over year, it could be a place to hold those funds across years. And also they can facilitate contracts for open source work. I don't know exactly what that would look like, but that is one thing that they could help out with. For my statement on the new JuMP branding is this implies that we need a new website. Since we have juliaopt.org, it'd be nice to have a JuMP website. We haven't really had one for JuMP. We had the GitHub page, so this is a high priority. If you know JuMP developers, if you know web developers, we now through NumFocus will be able to pay them. So come talk to me. And lower, yes, and lower priority. I'm just mentioning this because you might see it in the future. We may or may not come up with a new name for the GitHub organization, but there's not a big priority. And if you have ideas for that, we can chat about it.
Call it JuMP. Call it JuMP.
Is that taken?
Yeah, I just looked. JuMP.org.
Is it case sensitive?
What about the GitHub organization?
Oh,
The GitHub organization, that's what
how do I look at
Take it now.
I mean. You could even spell it out, you can just call it Julia from that program. The organization.
That's a long.
We can get JuMP.
Okay.
Get
Right.
it.
Yeah.
How do I do it?
Get it.
I don't know how I do it.
Question? Yeah.
How well does JuMP or can JuMP support GPUs or optimization? How does it work with GPUs?
So JuMP does not do anything with GPUs. It will just create the problem data and pass it to the solver, and the solver is welcome to use GPUs.
So every computation will be CPU, GPU interaction, essentially, where you have to send some updated information to the GPU.
If you're in do you mean in a nonlinear setting?
Actually, it is
Text
typing.
string generation or color.
Keep them out.
So for like linear programming, the problem data is you pass it once to the solver and there's no callbacks. If there is callbacks, then yes, it would need to go back to the CPU.
So for part of the issue of what NLP is not being updated, it's like issues on how to use the AD, how to use GPU. There's not a lot. I don't think anybody's really using GPU in constraint optimization. But if you have ideas, just let us know, because that's sort of the maybe JuMP 2.0 is no one else going to include those things.
Yeah, as far as I understand, the main restriction there that limits JuMP from being able to just have objects live on the GPU with whatever else the solver is like.
Because I saw vectors and
Is AD. It's the AD.
Yeah.
So JuMP doesn't have, for example, like array primitives or linear algebra primitives, which we talked about earlier today. So that ends up being a huge like blocker to kind of like dispatching on where the arrays you're handling live. So yeah, but that's something that we're hopefully once JuMP starts using more of the native Julia language ADs, like tools that exist, which is forever a bullet point on the wish list, then hopefully that kind of will be GPU support automatically, since we already have GPU support.
I would say, for now, that will be sort of, it's the NL interface itself that will be doing these things. I don't think anybody knows how would I use the conic interfaces to use GPU, so that's why in some sense the dictionaries are kind of not a big problem. Or
Okay,
will
so-
not be a big problem except for even for 2.0. Maybe 3.0 when we really figure out how to do things, it might be pretty
Maybe
complex.
aside, would it be enough to parameterize out the arrays and stuff, that way you can do GPU arrays?
So
That's why I have to cross the line because that's a.
yeah, this is meant to lead off an open-ended discussion, so I will start the open-ended discussion and with my talk. So thanks